Hello, calculus fans. Let's say that we have a point charge. Perhaps we have an electron sitting around in space. Coulomb's law will tell us that the strength of the electric field at any point, x, y, z in space, is inversely proportional to the square of the distance from the point P to the point charge. Let's ask two questions here. First, what is the rate of change of the strength of the electric field at the point 1, negative 2, 4 in the direction towards the point 2, 1, 7? And then part B, which is a more generic question, which is to show that at any point in space, the direction of greatest increase in the strength of the electric field is given by a vector that points towards the point charge. Essentially, that means wherever you are, if you want to increase the strength of the electric field the most, you should go directly towards the point charge. Now, for convenience, let's put the point charge at the origin. We know that the distance from the point P to the origin is square root of x squared plus y squared plus z squared. So Coulomb's law tells us that the strength of the electric field is equal to k times 1 over the square of the distance. And that works out to k over x squared plus y squared plus z squared. Go back to the statement of the problem to see what Coulomb's law says. It says that the strength of the electric field is inversely proportional to the square of the distance from the point to the origin. So what you see here in this expression is there is a proportionality constant, there is a square, and then the whole thing is in a fraction, 1 over the square of that. That's the inversely proportional part. Now, k is a proportionality constant. It has to do with the magnitude of the point charge. That is, are you just putting an electron at the origin? Are you putting 1,000 electrons? And it also has to do with a constant of nature, which is known as Coulomb's constant. We're not going to worry about the value of k. This is going to work no matter what sort of charge we put at the origin. What we're really focused in on here is the mathematics of what's going on. Let's first compute a vector that goes from the point 1, negative 2, 4 towards the point 2, 1, 7. We just subtract those points and we get the vector 1, 3, 3. That's a direction in which we're computing things. Now we need a unit vector in the same direction as v. The length of v is square root of 19, and so here is our vector now that points in the same direction as v, and this vector is a unit vector. Next, we need the gradient of the strength of the electric field. And I've rewritten this as k times x squared plus y squared plus z squared to the negative 1 power. So if we compute the gradient of E, this is what we get. We're computing partial derivatives of the strength of the electric field. And then if we plug in 1, negative 2, 4, we get this vector. So this is the gradient evaluated at the point we're interested in, which is 1, negative 2, 4. The next thing we'll do is compute the directional derivative. The directional derivative of the strength of the electric field is equal to del E dot U. U is a unit vector in the direction of our derivative, and del E we've already computed. That's the gradient of the strength of the electric field. So we're going to dot these things together now. And we end up with negative 14k over 21 squared times the square root of 19. This is a scalar. The rate of change using a directional derivative is always a scalar. The units for the strength of an electric field is newtons per coulomb, and then the units for the rate of change of the strength of an electric field with respect to distance is newtons per coulomb per meter. The last thing we want to do is go back and look at our gradient vector. Notice that if we take our gradient vector, we can factor out a negative 2k over x squared plus y squared plus z squared. And that means that the direction of greatest increase of strength of the electric field is toward the origin. It's toward the origin because if you're at a point x, y, z, then this vector here points away from the origin, but then you have to take into account the minus sign here. And then k is just a positive constant. So, any point that you're at, if you want to go in the direction of greatest increase of strength of the electric field, you should go towards the origin, towards the point charge. Okay, that's all for now.